I had written that like when you were like, we should write this up. But it's easy enough that I don't think we heard on. Yeah, I think silence. Yeah, like I think that's coming in like.
Okay, it's 2 o'clock, so let's get started. So we're continuing with our tutorial day for the workshop, and so up next is Pratyush Mishra, who's going to tell us about functional commitments. But let me just say that kind of the key topic is going to be on polynomial commitments, which are going to come up again and again and again throughout the week. So it's kind of important to absorb these ideas, and Pratyush is going to tell us all about them. So go ahead.
Okay. Yeah. Okay. The mic is on. Hi, everyone. Fantastic to be here. I actually got started in cryptography 10 years ago when I was an undergrad at Berkeley. I was at the workshop 10 years ago, but I didn't understand anything back then. And I think I'd like to think that I understand a little bit more now. Okay, awesome. Let's get started. So I'll talk to you about functional commitments. All right. Okay, so what are functional commitments and why do we care about them? Okay, so I think you already saw earlier today in Alessandro's talk a little bit about why we should care about functional commitments, but I'll quickly recap the reason we care about functional commitments, namely because you can construct succinct arguments from these. Okay, so just quickly recapping, right? The last few years we've seen a flurry of new means and mechanisms of constructing succinct arguments, right? And usually what they do is they combine some kind of information theoretic proof system with some very targeted cryptography. Okay, so this goes back all the way to Killian, who combined polynomial PCPs with vector commitments, and then over the last few years there's been evolutions of this approach, which changed the information theoretic component and the cryptographic component in a complementary way. Okay, so usually the change is basically you take your information theoretic component and you change the kinds of queries you can make, the verifier can make to the prover messages. And then you augment the cryptography to be able to support those queries. Okay, so you started off with PCPs plus vector commitments, that changed into IOPs plus vector commitments, and then linear PCPs with linear commitments, and so on and so forth. All right. So all of these are a general case or a special case of this more general paradigm of taking some kind of functional interactive oracle proof or some kind of functional information theoretic system, and combining that with a functional commitment. Okay, so at a high level, in this kind of functional interactive oracle proof, what the restriction is that the verifier can only make certain kinds of queries to the prover's messages, and the prover is restricted to sending only particular kinds of messages. Okay, and then we compile these down into succinct arguments by saying, okay, in the real world we can't actually enforce that the verifier only makes certain kinds of queries, or the prover only sends certain kinds of messages. So we're going to enforce that with a kind of functional commitment scheme. Okay? So this is where the cryptography goes, and that's what we'll focus on in this talk. I won't talk about the information theoretic component at all beyond this. Okay. So let's dive into how we define these objects. All right? So at a high level, functional commitments they're a way to commit to some message and then later prove that if I provide that message as input to some function, it results in a particular value. Okay, so some evaluation claim on that message is true. Okay, so a functional commitment scheme consists of 4 algorithms. There's a setup algorithm which produces the public parameters for the system. Okay, this might be private coin or public coin. It depends on the construction. You have a commit algorithm which takes the public parameters and produces a message, and a message and produces a commitment for you. You have some kind of opening algorithm, which is not like a standard commitment opening, but is a local opening, and essentially guarantees you or gives you a proof that some function of the message evaluates to this claim value. Okay, so some evaluation claim about the message is true. So here I'll denote, use alpha to denote kind of queries to the message. So you can think of it, for example, a point query. So this is saying, alpha of m, you can think of alpha as being, hey, the first index of m. So what is the first index of m? That is some beta. Okay? You can also think of alpha for the polynomial case as being, I don't know, view the message as coefficients of a polynomial, and alpha is an evaluation point, and I want you to evaluate this polynomial at that evaluation point. Okay? All right. So opening gives you an evaluation proof, which asserts that some evaluation claim is true. And then you can take this evaluation proof and check that indeed the claim is true. Okay? So just a little bit more diagrammatically, you do the setup in some kind of offline phase before anything is happened. And then you have these two parties, a sender and a receiver. The sender can use the commitment algorithm to commit to its message, and then later on invoke this opening algorithm to prove that the message satisfies particular evaluation claims. Okay? And then the receiver can take the commitment and this claim and the proof for it and check that whether or not the claim holds. Okay? Any questions? So this is fairly, I guess, maybe standard definition by now. Okay? You can also consider generalization where instead of having this kind of non-attractive thing where the proof only sends a single proof object to the verifier, you could have some kind of interactive protocol between the sender and receiver. And there are many schemes that actually live in this paradigm, but I'll just stick to the non-attractive case for simplicity in the rest of the talk. Yeah?
So in a polynomial commitment scheme, the message is a polynomial itself.
Yeah, you can think of the message as being the coefficients of the polynomial in whatever basis, Lagrange basis or monomial basis or whatever.
The function is the evaluation point then?
Yeah, so the function is basically specified or defined by the evaluation point, and the function is, let's say for univariate polynomials, compute all powers of your evaluation point and take the inner product with the coefficients, and that is your evaluation. Okay, yeah, great question. Okay. Is everything clear at this point? Okay. So this is the foundation that we'll be building off of. All right. So, okay, so I've given you the syntax. What kind of properties do we want from our functional commitment scheme, right? So the first is just standard binding, right? It's not really, you can't call anything a commitment if you can open it to two different messages, right? And so what we want to say is that no efficient adversary can open the same commitment to two different messages. And here we're talking about kind of global opening. So if I recommit to the message, and let's assume deterministic commitments for the moment. If I recommit to the message and I get the same commitment, then it better be the case that M1 and M2 are indeed equal. Okay, so this is standard binding. I won't talk again too much about this. The interesting stuff comes when you start.
Sorry, but is that, well, I guess it depends on the hiding, but you're okay with deterministic, usually commitments are probabilistic.
Yeah, so normally we think of commitments as randomized to give you the hiding property. I'll talk about hiding briefly, but actually for many arguments, for many applications, we don't necessarily care about the hiding property. If you want to make this true even in a randomized world, you can just pass the randomness as explicit input as well. Okay? Yeah?
I mean, by the usually one, like, you want to talk about the opening, but wouldn't convince you, you don't want to be able to open the same.
Yeah, so that's what this is saying, right?
You're opening to some evaluation.
So this is just binding for the whole message when I open the full commitment. We'll also come to talking about kind of this local binding when I give you only local openings. So that'll be on the next slide. It's a great question. Okay. Yeah, so binding is standard. I guess the interesting properties come in when you start talking about proving things, right? So there we want completeness, which says that if I commit to a message, right, and then produce a evaluation claim honestly, so indeed the committed message, when I pass it as input into alpha, it leads to beta, right? Then the check algorithm should pass, okay? And we'll go for perfect completeness. In general, most of our constructions can achieve this. But you could consider a more generalized version, which has some completeness error as well. This sometimes shows up in lattice-based constructions. Okay, so yeah, nothing too interesting with completeness. The interesting part comes in when we talk about kind of the soundness case, okay, when we have some dishonesty. Okay, And the relevant notion here is what's called function binding. Okay? And the intuition is that we want it to be the case that if I give you local openings for the same commitment at a bunch of points, it better be the case that they're kind of consistent. So if I give you, if I open the same message at the same point, it better be the case that I can't produce two evaluation proofs which assert that, okay, in the first case it was evaluating to beta 1, and the second case it evaluated to beta 2, for example. Okay? So you can write this out formally, but basically the idea is that you have some adversary which can produce many evaluation claims and evaluation proofs. And we want it to be the case that if all of these proofs are valid, then there must exist some kind of message which is consistent with the evaluation claims. Okay? You can think of like the simple case as basically there's two of these claims, right? And they're both for the same alpha. It better be the case that the betas are also equal, right? It should not be the case that alpha of m equals beta 1 and alpha of m equals beta 2 and beta 1 is not equal to beta 2. Okay? That's what we want to prevent, and that's kind of what this definition is going for. Okay? Any questions?
You also going to talk about extraction?
Yes, so that will come in just a second. Okay, all right. So if you want to be concrete, you can think of this, for example, if you think of Merkle tree, right? What this definition is saying is that I can't give you two Merkle paths, both of which are valid with respect to the same commitment, yet they open to different leaves. So A is not equal to B, right? This probability should be negligible. Okay? All right. Okay, so this is a definition, right? Is it actually useful? Let's try to figure out what kind of properties it gives us. All right? So the thing that we get from function binding is we get some consistency of local views. Whatever locations have been opened, we know that they're going to be consistent with each other. There's not going to be any contradictions in the evaluation claims there. Right? But what it doesn't guarantee us is any kind of global consistency. Right? So if you think of this Merkle tree example, right? This is a Merkle tree, right? But this subtree is missing. And in particular, there's no valid opening for M4 or M5. Okay, so we don't have any guarantee that this full message actually satisfies particular properties. It could be garbage in particular locations, right? As long as those locations are not opened, we don't get any guarantees about those those unopened locations. Okay. So it's very easy to see in the case of Merkle trees. Sometimes a little bit more difficult to see in the case of other kinds of functional commitments. Okay.
So I have a question. Even before extraction, I mean, you could have defined it to say not only there does not exist M like that,
that's inconsistent.
there does not exist M that commits to the commitment, to the, I forgot the name, to the whole thing such that. But you didn't do it because it's harder to achieve, right?
Yes, it's harder to. So this is like kind of the minimal guarantee. So if this definition does not say anything about, okay, this commitment actually does commit to this particular message. And that's because essentially at that point you're at extractability in some sense.
Exactly.
So we don't try to relate this commitment to whatever message is consistent with it because there might not be any such message. Yeah.
But you can have something in the middle, right? So you commit to something either a bottom or a message, and the bottom will remain the bottom, right?
Yeah, so you could try to go for that. I think, I don't know if people have considered that notion where you get this kind of partial opening that whatever is unopened is like guaranteed to be an error or something like that. Yeah. Okay. Yeah.
Because there's another definition that for like every alpha, you should not be able to open it to two different betas. And
Yeah.
For some functions, they're equivalent, but I guess for all the things you care about, are they going to be the same as this definition?
Yeah, so normally we care about very simple functions like linear functions or point queries or polynomial evaluation queries, and then they tend to end up being the same. Okay. Yeah.
So in the other slide, so you said that you cannot, they may not be M4 and 5, but if the function h is surjective, which is typically the case, it may be hard to find M4 and M5, but they do exist.
Oh yeah, they will, I mean, yeah, you will have some collisions, so there will probably be some pre-image here. but the adversary might not have such a pre-image in mind, because we're talking about efficient adversaries.
So it's about the finding, it's not about the existence, it's not
Yeah,
about
sure.
the
Yeah,
finding.
yeah, yeah. So yeah, this should say difficult to find. Yeah. Yeah.
But you're saying current definition is not efficiently falsifiable, but for normal cases it will be efficiently falsifiable. Is it the resolution? There is no way to prove there exists no message, right? Even here, right?
Yeah.
I mean, it's sufficient to prove that you break local binding, but even if you don't break, I don't know if the function h doesn't, right?
Yeah, it might not have a pre-image in this location or something like that.
And you okay with it? Okay.
Yeah.
But can't you reduce global binding to local binding via things like linearity tests?
Yes, but then that gets a little bit more involved, and then you essentially end up with some kind of extractability guarantee there, usually via rewinding. So you could try to say, okay, I'm going to ask you queries for every location. Once I have the commitment, I'm going to rewind you again and again, and then you can extract like a global view. But then you might just get like, okay, this location is bought. The adversary cannot open particular locations still. But if you add on like a linearity test, some kind of probabilistic check, then you do get this kind of global structure guaranteed as well.
That's from a feasibility perspective. If we want to get the minimal possible assumption, maybe we want to make the minimal security notion that can be bootstrapped into something.
Yeah, so that's why we're going for function binding. So we'll see this extractability and function binding, they tend to rely on different kinds of assumptions. Okay, wonderful questions. Anything else? Any more? Okay. All right, so we talked a little bit about, this local to global things. Maybe let's actually talk about what kind of global, what some kind of global security would even mean, right? So here we normally go for this notion called extractability, right? And what this says is that now we actually do kind of link this commitment to these openings, right? So we want to say the commitment contains a message, in some sense, that is consistent with whatever openings have been given to you by the prover. Okay, so we formalize this via an extractor, which we'll just see in a second. And there's usually two main kinds of extractability that people consider for functional commitments. Okay, the first is non-black box extraction, which just says that for every adversary there exists some extractor, some efficient extractor, which this should say commitment, which takes out, which gets the commitment from the adversary and is able to produce some message. Okay, and this message should be consistent with whatever evaluation claims the adversary is making. Okay. So it's important to note that here that we're not extracting after we see the evaluation proof. The extraction happens kind of even before any evaluation proof is produced. Okay?
Extractor is not taking the random coins with the adversary, nor a tractor.
So it depends on the, I omitted some things for clarity, but yeah, so this adversary does, this extractor does depend on the, it's non-black box in the adversary. Yeah.
So if you had here alpha to be an arbitrary subset of points, for example, so if A sets alpha to the empty set, then the proof is trivial. There is nothing to prove.
There's nothing to check.
Also in that case, you expect the extractor to...
So the extractor can output whatever it wants in that case, right? So then there's nothing to check on this side, right? So kind of it's trivially satisfied, right? So the interesting case is when the adversary makes some claim and the claim is valid, yet the extracted message does not agree with the claim somehow, right? So that's when we say the extractor has failed. If the adversary doesn't make any claims, it just outputs an empty set, then there's nothing, we can't check what the extractor is doing at all.
Okay, so it doesn't have to be consistent with the commitment. There is, in that case, there would be no property about that.
If the adversary makes no claims, I can just throw out a commitment in the world and you can try to extract from it, but it's not really useful. I'm not making any claims about it, so I'm not trying to be malicious in some sense. Yeah?
If only one claim here, does it?
Yeah, you can generalize this to multiple claims.
It's not immediate that one does not imply many immediately.
Yes, that's a good question. I think for polynomial commitments, at least I know that it does. I think, yeah, if you assume certain properties of your commitment scheme, for example, homomorphism, then you get very nice batching properties as well. But I think there are actually reductions. You can just reduce the multi-claim case to the single claim case as well, like maybe with some union bound or something like that.
Let's choose on red.
Only locally consistent, but not globally.
Okay, any more questions? Okay, all right. So this is kind of a definition that you would use when you want to prove things in a standard model. You can base it, you can realize this definition, for example, by relying on particular knowledge of exponent style assumptions, right? And you could prove this. People have also considered extractability in idealized models. Okay, so think of it as like the random oracle model or the GGM. Yeah.
Sorry, if that's all you require, assuming A is deterministic, what keeps the extractor from simply running A, getting alpha and beta, and then simply solving alpha of n equal beta?
It won't be consistent with the check.
So I didn't quite catch the question. So you're saying the extractor runs A also for this point. So A is like...
So the extractor knows alpha and beta. You can assume that if A is deterministic, the extractor can simply run A and get alpha and beta. So why is it important that it's done before?
So actually, you can think of these as like two different adversaries, and the extractor depends only on this adversary. So this is like A1 and A2, and the extractor depends only on A1. So yeah, that's maybe something I missed on the slide. Yeah, but the extractor depends only on this first step adversary, and the second step adversary is kind of not known. The extractor does not depend on it at all.
Why?
No, I think the point is, I think there's an error. The extractor gets the commitment. The commitment is fixed. He doesn't get to choose it.
No, I think I'm just confused about the A.
Yeah, this should be A1 and A2. So the extractor depends on A1, but not on A2.
It should work for all A2.
Yeah, it should work for all A2.
A2 is not known. Yeah.
Does it take the commitment as input or no?
So if it depends on the extractor, or if the extractor depends on A1, then you can just run the adversary and compute the commitment. So you can pass it as explicit input, but if it's deterministic, you don't need to.
You assume that A is deterministic?
I think if you can make it work with randomized as well. It's not necessary for it to be deterministic.
But the point is, the point that the extractor gets the commitment as input. That either way, that's kind of the...
You just assume that the extractor has the commitment here.
What does A2 see? Does A2 see the commit?
Sorry?
What does A2 see?
A2 is like, it gets past some state from A1. So it is gets past some auxiliary information from A1, which allowed A1 to produce this commitment. Whatever that information was, A2 also gets that. Yeah, maybe I was a little bit too brief in writing out this definition. Okay. Any more questions? Okay. All right. So coming back to straight line extraction. So here we kind of can go back to black box extraction, and even stronger than black box, right? So here we say there's an efficient extractor which works for every efficient adversary. And what we do now here, again, you can think of this as A1 and A2. But now the extractor kind of does not depend on the adversary. All it gets to see is kind of the input-output, the query answer trace to whatever oracle the adversary has. So if it's a random oracle, if you're working in the random oracle model, the adversary made some queries to the random oracle, and whatever those queries and answer pairs were, the extractor gets to look at that trace and has to produce the message from that. In the GGM, it gets to look at the GGM queries, and based on that, it has to produce this message.
But it also has the code of A, right?
You could consider like a combined one where it has both of these, but usually when we go for straight line extraction, we don't need to depend on A, at least in the
idealized model.
Yes, in the idealized model. So this is usually we work care about this and can prove things here in the idealized model, in some idealized model. Yeah.
Sorry, so what is the oracle here? Like,
you can think of it as some random oracle or the generic group oracles. So that's what these oracles are. And this trace is like the query answer trace to those oracles.
So every function here except for E should have oracle access to F, right? You wrote it only A sub F, but everybody should have the second A2 should.
Yeah, this also should get access to F.
Check should have setup.
Setup doesn't necessarily, but it depends. Yeah. Yeah.
But the check, for example, should.
Yeah, I think the key difference is that E does not. It only gets this query answer.
But the function class cannot depend on f, right? Alpha and beta cannot depend on f.
Usually we fix it beforehand. So it's kind of, it depends. If you're working with GGM, for example, then your function class is queries to polynomials, right? So polynomials depend on the order of the group. So there can be some dependence there also. Yeah. Okay, how are we doing on time? Okay, kind of halfway through. All right. Okay. Any questions about these definitions? Okay. All right. So the nice thing is that both of these variants, they do imply function binding. Okay. So it kind of comes from here. All right. So it's kind of a strictly, you get strictly more guarantees from extractability. Okay. So then the question that arises is, why rely on function binding when you can just extract, right? When extractability gives you these nicer properties, right? And unfortunately, it's because these stronger guarantees come at some cost, right? You get this nice consistency of global views, but usually by relying on some kind of non-falsifiable or idealized assumption, okay? So for example, when talking about Merkle trees, if you care about position binding, which is basically function binding for point queries, you can get function binding just from collision resistance, okay? But to get extractable Merkle trees, you actually need to rely on the ROM, or at least we think so. We don't know of, as far as I know, weaker proof, okay? Similarly, for the KZG10 polynomial commitment, which is one of the simplest polynomial commitments, you can get evaluation binding from a falsifiable assumption, this Q power strong Diffie-Hellman assumption. But extractability, we usually have to rely either on some kind of Q power knowledge of exponent or analyze the protocol in idealized models like AGM or GGM. Okay? So kind of you get the stronger power, but you pay for it in terms of the assumptions that you have to make. Okay? So the question then you need to ask yourself is, does your application actually need the stronger guarantees that extractability gives you, right? Can you get away with the weaker guarantees? And it turns out that for many applications, you don't need extractability. It can give you some benefits in terms of your analysis, but if all you care about is, can I realize X from Y, you might not need extractability. So even succinct arguments, so this is kind of what Alessandro covered earlier, but we'll briefly recap it here. Okay? By taking a look at kind of the history of how we constructed or proved this FIOP plus FC equals SARG formula, right? So the earliest stuff, again, was Killian, and all of these early works, they kind of relied on just position binding for Merkle trees, okay? But then when we moved to IOPs, I guess we analyzed this in the ROM to get extractable Merkle trees, right? And similar things happened with polynomial IOP-based constructions. We analyzed them with extractability, kind of this non-black box extraction definition. But today, now we know that actually function binding suffices even for these kind of more exotic polynomial, more exotic functional commitments. Okay, you can prove this recipe directly from this function binding of your underlying functional commitment. You don't need to go all the way to extractability. Of course, there are some benefits of extractability. So you can get, for example, straight line extraction without having to rewind anywhere in your security proof, whereas the function binding proof does rely on rewinding your adversary. So the extractor is a rewinding extractor. But on the upside, you get falsifiable assumptions, which at least we don't know how to do on this side. Okay, and what people do in practice is to just do both. Okay, so you analyze in this, and then in practice, actually, people just say, okay, we don't really care about security that much, so we're just going to go from the extractability-based, whatever extractability gives us. Yeah?
On the right-hand side, you also can get an argument of knowledge, right? With extractability.
Yeah.
Yes.
Which you cannot on the left. And that's
You usually can still, like, the rewinding extractor does kind of give you enough information to reconstruct the witness as well. It's like even the proof here, even if you care about soundness, does rewind enough to actually get out some kind of.
But what do you mean? If it's not interactive, then you can't rewind even.
So what you do is the succinct argument. This is the argument case.
Yeah. So you assume if it's interactive, you can rewind and then you can extract. Or you rely on random oracle.
So this, I'm not sure I understand. So here we're talking about the argument, right? So there's like some interaction between the, we've replaced all of the oracle messages with these commitments, and then at the end there's some opening phase. So that entire interaction process is what I'm talking about here as rewinding. So you have to rewind that entire argument prover.
I see.
And that underlying reduction relies on function binding, which might or might not be interactive or non-interactive.
Okay.
But this rewinding here refers to the argument extractor.
You assume that your prover is going to answer every open what you ask him to, and that's how you write.
Yeah, at a high level.
Mm-hmm.
with some probability.
Yeah, with some probability. Okay, yeah.
So I see how, so in one case there exists a function, in the other case you can actually, a method, in the other case you can actually recover it.
Yes.
I'm not sure I understand why you call one local and the other one global. What exactly is local and global?
So here, I guess like it's maybe more of an informal idea, but the thing is that when we come back here, right? If I don't open at this location, I don't have any, and this might be garbage, right? But extractability says that the moment you give me a commitment, there must be some kind of underlying message at every point, in some sense.
But you're not proving anything about those positions.
Yeah, it might.
Just giving a message.
Yeah, so it might not be consistent, but I get out like some candidate message. And if in the future you're able to produce a proof about that location, it must be consistent with whatever I extracted. Okay? All right. Okay, so we have roughly 25 minutes. Okay, so this is extractability versus function binding. Yeah, so the takeaway is essentially, it's, on the road to extractability, you end up proving function binding almost always. So just do both, and then your application, it might be interesting to analyze or try to prove security from both function binding and extractability, and then you use whichever one is more convenient for whatever you want to do. Yeah?
We expect that constructions which only satisfy function binding might be more efficient in practice.
That's a good question. I think there's no I wouldn't say there's like a particular rule in either way. And sometimes the two just coincide. Like, for example, for inner product arguments, like bulletproof style things, the two are almost identical. Like, you don't really have much difference. In some cases, you actually do end up with the extractability case being more inefficient. So for example, if you try to prove KZG from power knowledge of exponent, there your extractability requires you to have extra commitments. But if you care only about function binding, you don't need like the extra group element in the commitment.
But extractability is an assumption. You can assume that you can extract. Many of the assumptions just assume. It's like knowledge assumptions.
Yeah, so like for example, KZG is essentially just the commitment is just AGM directly almost. Yeah, so that's why these idealized assumptions, these non-black box assumptions, are maybe why you want to try to prove things from function binding if you can. Yeah. Okay. Awesome. Okay, there's also, just briefly mentioned, I won't talk about it again, there's also a kind of third notion of extractability for functional commitments, which kind of views this commit open check process as itself an interactive argument. And you just you make it interactive by having the receiver send some kind of query, okay? And then you analyze kind of extractability of this interactive argument by trying to construct a usually rewinding extractor here, okay? Kind of, this is, I would say this is like a more messy notion to work with, especially once you start putting it inside your argument extractor, for example. You have like an rewinding of a rewinding, and it kind of gets messy. So people usually just tend to work with the first two notions, but this is something that you can do also. But okay, all right. that's all I say about extractability. Any more questions, or should we move on? Okay. All right. So I did promise to say something about hiding. Yeah, commitments normally are hiding. In applications arguments, they don't need to be, right? But if you want zero knowledge, you usually do need some kind of hiding property also from your commitment scheme. Okay. And the guarantee that kind of you want informally is that the commitments and openings, they reveal no information about the message beyond whatever your evaluation claim gives you. So you learn inevitably that the committed message at alpha evaluates to some claimed evaluation, right? But everything else should be hidden, okay? And you can formalize this in terms of perfect hiding, statistical hiding, computational hiding. All of these are things that you can do. For a lot of the constructions, we can actually just get statistical or perfect hiding. I guess one more thing is that this only really makes sense if you bound the number of queries the adversary, like the number of evaluation claims the adversary can get. Because if you, at least for many function classes that we care about, if you get enough query answer pairs, you can just reconstruct the message. So for example, point queries, if I just query for every point, I know the entire message, right? Or polynomial queries, if I just query enough evaluations, I can interpolate and reconstruct a polynomial. So yeah, you really want to, this only really makes sense when you have like a bounded number of queries that are being considered. Okay. Yeah, usually constructing, it's not too involved to show hiding for polynomial commitment, or for many functional commitments. But I won't talk about it too much more. Okay, so that was the definitional kind of foundation of functional commitments. Let's take a look at some constructions and see, what these notions actually mean in practice, right? So when we're talking about constructions, we care about like a number of different metrics. Okay, so there's lots of different dimensions along one which could try to optimize the construction, right? So you could try to use different kinds of assumptions, such as hashes versus discrete log versus pairing versus lattices. You could care about setup type, like do you actually have public coin setup or private coin setup? You could care about efficiency of the various things that appear in the definition, right? Like commitment sizes, proof sizes, the size of your commitment key. This is also an important metric for a lot of applications. Committing time, opening time, verifying time, all of these things are kind of important things that lots of different constructions, they pick, okay, I'm going to optimize for committing time, and then they just go all in on that, to the detriment maybe of proof size. Okay, so this has basically resulted in a huge proliferation of constructions, okay? So this is like in the last, I would say, 10, 15 years. And this is not even a complete list. There's probably like 10 more here and 10 more here. So there's like a lot of different constructions which optimize along different dimensions. So maybe the question that we want to answer for the rest of this talk is, what kind of FC schemes should we focus on? Okay, so what kind of, like, let's say we try to filter down by query class. Okay, so the nice thing is that there's kind of reductions which allow you to go from one way to the other for many of these query classes. So if I have point queries, I can emulate that with a polynomial commitment by interpolating my message as a polynomial. And then the point query becomes just a polynomial evaluation. And you can do the same thing for all of these directions. Okay. So again, they kind of are, this doesn't really help us trying to filter down by query class.
Sorry, why isn't it helpful? Let's say I need a polynomial query. How do I do it with point query?
So you normally okay, so how do you, see this goes via IOPP. So I encode my polynomial via some kind of error correcting code, and then I invoke something like, say, some proximity test like fry plus some other IOP, like say some check.
Okay, but then still I need to, sorry. Oh, you're saying you do like a proof of proximity.
Yes. Yeah. Okay. So you have to add in some information theoretic component there, but then you can go from your polynomial queries down to just queries into your IOP oracles. So all of these kind of query classes, in some sense, become equivalent, except in terms of efficiency. So you might lose efficiency going in one direction or the other.
Round complexity also, no?
Yes, and so all kinds of metrics, so round complexity, proof size, prover time, all of these things. Like, you might want to stick to a particular if you're constructing natively a polynomial commitment, maybe it's best to work with polynomial IOPs, for example.
Okay. This regardless of extractability or binding property.
Yeah, so normally this reduction will invoke some kind of information theoretically sound additional component, so like say sum check or something like that. So that will increase error, but not from a computational assumption.
Oh, what I meant is that if for one of the two you have extractability, then you preserve the extractability. If you only
these reductions tend to
binding,
these reductions tend to preserve extractability. Function binding also, I think, should be preserved, usually because these reductions invoke just information theoretic components and not much cryptography. Usually no
the same
cryptography.
reduction that can be applied to both.
Yes, yeah. Okay. All right. Okay, so given that all of these are kind of similar, I'll choose somewhat arbitrarily to focus on PC schemes, in part because there's been a lot of work from both say polynomial commitment schemes. There's been a lot of work in both industry and academic research on constructing increasingly more efficient versions of PC schemes. Okay, and oftentimes the constructions and analyses tend to be relatively simple. So we'll look at least one example. I don't know how much time I will have, where we will go through everything, including extractability, and show that everything will just fit on like 3 slides. Okay, all right. And because there's a plethora of constructions that kind of achieve almost every point in the trade-off space that we saw before. Okay, and in contrast, for vector commitment schemes, you don't really have that many unless you kind of follow one of the reductions, right? And it seems that kind of we're stuck in some kind of local optima of using Merkle trees there. Okay, and linear commitment schemes, linear queries, they come with this caveat that linear queries, you need to specify the linear function. That's usually results in non-succinct systems. Okay, so we'll focus on PC schemes. Okay, so the first construction we'll see is kind of, I would say, in my opinion, one of the most beautiful constructions. Is very simple, elegant, everything fits on one page. Okay, and it's also simple to analyze. Okay, so this is the KZG polynomial commitment scheme. It appeared at Asia Crypt. And it supports univariate polynomial queries, and it relies on assumptions in pairing-friendly groups. Okay, the setup type is unfortunately private coin, but it's not too bad. We have figured out in practice how to get around this. Okay, and it has really, really good efficiency. So commitment size is just one group element. So if you take standard pairing-friendly groups today, this is on the order of, let's say, 96 bytes or 48 bytes, if you compress or not. Okay, the same thing with your evaluation proofs, just one group element. The commitment key size is large. It is linear in the size of your polynomial that you want to commit to. Okay, so in the degree of the polynomial. And both committing time and opening time are relatively fast, is a multiscalar multiplication of the degree of your polynomial. But we know how to do this very efficiently nowadays. Okay, and checking is just 2 pairings, so it's independent of the degree. So it's very, very efficient. Okay. Oh, did I skip something? What happened here? Okay. Okay, so this is the construction on just one page. Okay, so the setup, I basically take my generator, I sample some random scalar, and my commitment key is basically powers of the scalar encoded in the group. Okay, so it's g, gamma g, blah, blah, gamma to the L minus 1 g. Okay, and my verification key consists of some small constant size information. Okay. To commit, I basically just take the inner product of my polynomial with this commitment key. So you can kind of, H is the generator for G2. So this is a pairing-friendly group. So G is the generator for G1, and H is the generator for G2. Okay. So the commitment, you can kind of just view it as, evaluating your polynomial on the secret exponent gamma. Okay, that's your commitment to your polynomial. And opening relies on this identity, which basically just says that, I think it's on this page, so you can ignore the title. Okay, it says that some polynomial evaluated alpha equals beta if and only if there exists another polynomial q of this form. Okay. This is the identity that we'll rely on. And that's how we compute our opening proof. We basically just commit to Q. Yeah?
Beta must be appearing in the identity, or am I confused? Can you go back to the...
This beta is a publicly known field element. So here, we're saying F evaluated at some public evaluation point results in some public evaluation claim, some value that is publicly known to both the prover and the verifier, to everybody in the system.
I think the comment is we should say fx minus beta. Not
Oh, yeah. Oh, sorry, yes. This.
No, the numerator.
This
Fx
up here.
minus beta.
Yeah.
Okay.
Yeah. Sorry. Yeah, good catch. Okay. Actually, I optimized a little bit here because it turns out in the division you can even omit beta. But the point is that we commit to Q. We compute Q, which is just one polynomial division. It can be done in linear time if your divisor is sparse. And so you commit to this guy, and that's just one multiscalar multiplication, just like the commitment. Okay? And checking is basically one pairing, or two pairings. Okay? This is all KZG on one slide. Okay? So commitment binding just kind of follows similarly to binding for like the standard Pedersen commitment. But instead of reducing to DL, we reduce to this Q power strong Diffie-Hellman assumption. I'm not sure going through the math is that illuminating. But I guess completeness again follows directly from the identity that we derived before, or that we talked about earlier, right? In some sense, we're just checking that the identity holds in the exponent at this point gamma. And if the evaluation proof was computed honestly, then it will hold for all the choices of gamma. Okay? Any questions? All right. Okay, so function binding is a little bit more involved, but again, we reduce to this strong Diffie-Hellman assumption. And the idea is that if we have two evaluation claims which are contradictory, so for the same alpha, this evaluates to two different betas, right? If they both pass the validation inside the check algorithm, then after some algebra, you can rewrite it, and you get this kind of expression, okay? So you get something which you can write it out to be, which will give you this. Yeah, maybe I shouldn't have put so much math on the slides. But the point is essentially is that if you write out the reduction, if you write out the arithmetic, you will get out this claim, which will directly be a break for your SDH assumption.
This is not enough information. What if I give you two L points that don't correspond to a degree L polynomial?
Yeah, so you need to handle the case. But this is, I guess I'm handling, for the slides, a very simple case where there's only 2 points. Yes. You have to be, when you have multiple evaluation points, you need to be a little bit, do a little bit more work there. Yeah. I think if I put the general case, then it will be even more incomprehensible. Okay, all right. Yeah, that's it for KZG. So the point I think I wanted to make here was just that the description fits on one slide, and arguing about all these properties fits on one slide. Extractability follows if you just analyze in the GGM. It just, like this commitment, whenever the adversary gives you a commitment, it'll also give you some kind of, for example, some trace of the Oracle queries, and that will correspond almost directly to the underlying message. So we kind of assume away extractability. Okay. All right. So the next construction we'll see is this construction, which maybe was one of the earlier constructions for polynomial commitments, and it follows from like our favorite trick as cryptographers, which is basically to put everything in matrix form. Okay. So instead of trying to do linear work, we try to chop up our message and represent it as a matrix, and then we manipulate this matrix to get some non-trivial efficiency gains. Okay. So that this PC scheme has some nice properties. For example, it supports both univariate and multilinear queries. You just need to change a little bit in how you go about inside your opening and checking algorithms. Okay, it just relies on discrete log. There's no need for pairings here. It has a public coin setup, so you don't need to embed any secret in any exponent or anything of that sort. Okay.
Sorry, can I ask you a question?
Yeah.
this polynomial commitment, can't you make it like multivariate as well by just kind of doing similar thing but over multivariate? Like
yeah. So instead of putting, so this is the PST commitment scheme, and instead of putting kind of univariate monomials here, you can put multivariate or multilinear, whatever you want, and that also works. This opening algorithm was a little bit more complicated because your identity changes, but that still works. Yeah, you can make it work. Yeah.
Always much better ways to do it.
Yeah, to do it.
Yeah, so now we actually have reductions which you don't need to actually put different kinds of monomials in the SRS. You can just put, you can actually just reduce multilinear queries directly to some checks over your univariate polynomial commitment. Usually it's kind of like another reduction from multilinear to univariate, some information theoretic style reduction.
I see. So you go from multi to uni by just another.
Yeah, you don't even need to change the commitment scheme.
I see.
Yeah. So this is Gemini as well as some recent work, Zero Morph, Mercury. There's a bunch of work in the last 3-4 years which does this. Yeah. Okay. All right, we have 7 minutes. I'm not sure we'll get through this, but okay, let's try. Okay, so this matrix polynomial commitment, it basically gets these nice properties by giving up on some efficiency. So your commitments are now square root size, your evaluation proof is square root size. You get a better commitment key size of just square root again. Commitment time is similar, opening time is similar, but now opening or checking is not succinct or not polylogarithmic anymore. It is square root. Actually, this I think should just be one square root sized MSM, not square root L many. Okay, so you get some non-trivial efficiency gain. You're not having to do linear work to check the evaluation claim, but it is not 2 pairings. Now it's square root sized MSM. Okay, so the key idea roughly is just to write your polynomial as some square root by square root matrix. Okay, so you take your coefficients, you line them up in this way, kind of in row major order, and then every evaluation query kind of becomes some vector matrix vector query. Okay, here you just have 1 through square, so m is the square root of L, so you just have 1 through square root powers, and here you have in strides of z to the m. Okay. All right. The scheme is a little bit more complicated here. Setup is basically just your Pedersen commitment setup. To commit to your polynomial, now you commit to each row of this matrix, and that gives you square root many Pedersen commitments. Okay. So that's so far so simple. Okay. To open, it's a little bit more complex. What you do is you write your polynomial again as a matrix, and you only perform one side of the multiplication. So you multiply your matrix from the left by this vector, 1 through alpha to the m squared-ish. Okay? And your evaluation proof is just this vector of field elements now. Okay? To check it, what you do is you rely on the homomorphism of the commitment scheme. Okay? And the idea is that now if I take these commitments, these square root many commitments, and I linearly combine them with this same vector alpha from the previous slide, right? That should be actually a Pedersen commitment to the vector which was inside my opening proof. Okay? Okay, it's a little bit difficult to see. Maybe I won't elaborate on it, just so I can leave some time for questions. But yeah, I guess completeness follows from the homomorphism, and function binding actually also just follows from the binding property of the underlying Pedersen commitment and the homomorphism property of the commitment scheme. So I think actually that's it from me. There's some open questions, which I think would be lovely to answer. Some of these are copied from Giacomo. But yeah, there's like a lot of open questions in constructing new kinds of functional commitments as well as definitional aspects, right? So I won't go through all of them here, but the broad strokes are, can we construct better kinds of post-quantum functional commitment schemes, vector commitment schemes, for example? Can Can we reduce the need for private coin setup and just get public coins while preserving all the efficiency benefits? So, really small proofs, really small commitments. Can we do the same thing, again, by relying on post-quantum assumptions such as hashes or lattice-based assumptions? Going back to this reduction between the different query classes, can we describe reductions which are, say, alphabet preserving, so you don't have to, when you encode with the error correcting code, can you use good error correcting codes which preserve your alphabet size? Can you reduce the round complexity of these reductions, and so on and so forth? Okay, so there's a lot of exciting questions, and these have a direct impact on systems which are being deployed in the world today. Like, so your improvement here directly improves the proving time, efficiency, verifying time of the succinct arguments that you get from these constructions. So yeah, I think it's an exciting area to work on, and yeah, it'd be lovely to have all of your energy in this area. Okay, thank you.
Great. We have time for a few more questions. So I have to ask you, maybe it's a leading question, but what's the shortest commitment scheme, polynomial commitment scheme we have today?
I would probably say KCG, although it depends on if you're talking about the evaluation proof as well. Then I would say it's, as far as I know, still KCG.
So, or let me generalize your question.
Yeah.
Today, if I want to do a polynomial commitment, is it clear that in terms of efficiency, globally speaking, discrete, like group-based is the way to go?
It's even pairing-based.
Pairing-based.
Which is the shortest he was mentioning, yeah.
Yeah.
Yeah, I think among the constructions that we have, that is the state of the art. You can try to
in industry. So you're asking specifically about shortness or best?
Shortness, sure.
Proof size, I don't think you can do.
No, but how about efficiency?
In terms of like what the industry is using, I think to a large extent we're based schemes.
So the methods we'll talk about tomorrow morning. That's kind of what's used in the industry, because the prover time is much faster.
Yeah, so there's, okay, till recently it was also the case that these small proof size ones like KZG tended to have usually close to best prover times, but in the last, I want to say 3-4 years, that has changed. And now the hash-based, I would say hash-based schemes, which kind of combine some error correcting code with your Merkle tree, those have become probably best in terms of committing time and opening time, and even in checking time recently.
So do you think there's any hope of getting a post-quantum polynomial commitment scheme where the evaluation proof is as short as what we get from KZG?
I think that would require directly kind of answering this question here. Well, or from lattices. Yeah. I think like lattice-based ingredients tend to have larger sizes than group-based equivalents, so I don't know if lattice-based stuff can get us there. Yeah, I also don't know if Merkle trees, there's much improvement that you can have there either. I think there might also be particular lower bounds, at least in the ROM, on this front, but yeah, maybe you need to go into some kind of computational assumption from lattices to improve there. Yeah.
Cool. Any more questions? Yeah, please.
Yeah.
So when people come up with a new SNARD, they have some FIOP and some functional commitments. How much choice is there in the, like it looked like there were a bunch of choices for functional commitments. How much choice is there for the FIOP versus the other one? And like,
yeah, people are innovating on both fronts. So there's lots of new constructions of FIOPs, but they usually tend to fall into you're constructing things as a polynomial IOP. People tend to not do linear IOPs, and even when constructing the standard IOPs, they tend to obtain those by compiling PIOPs down via some kind of error correcting code plus proximity test. Yeah, but yeah, there's like a lot of constructions people are innovating. There's all kinds of properties you want there also, such as reducing the number of oracles you're sending, reducing round complexity, reducing, yeah, like even what kind of, like how dense or how big the coefficients are inside your oracles. You want zero-sized or small integer-sized oracles or elements in your oracles and so on and so forth. So like there's a lot of activity on both sides of the ingredient. I didn't talk about the FIOPs, but yeah, there's lots of interest and activity on that front as well.
Cool. Any more questions? All right, thank you. We'll reconvene at 3:30 when we'll talk about folding. Relation and folding.